A common application often deals with temperature in some way. And so in these instances, we want to rely on what's known as Newton's law of cooling. So what that law says in general is that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. So a lot of familiar terminology in there. Yet again, we see the word rate, and we also see proportional to. So one thing I do want to point out is, of course, it says cooling, but you can really use this setup with either heating or cooling, because in the instance of cooling, we expect to get a solution that is decreasing, so a negative proportionality constant. But I could also have heating with a positive proportionality constant to reflect that increase in the rate in the solution function. So an example here where we're dealing with temperature is we're talking about a dorm room where we know that it starts at 76 degrees Fahrenheit at midnight. Then the power goes out and the temperature is measured at 2 further times. 1 a.m., well, I guess it's only measured at 1 a.m., and we want to see what it will be at 7 a.m. So the word temperature there is really what tips me off to think about the assumption of Newton's law of cooling. So one thing we can think about here is trying to identify some of the things. The object is the dorm room in some sense. That's what's changing temperatures. And when we talk about the surroundings, in this instance, that's outside. So we're given the temperature of outside. That's the surrounding temperature. So according to the Newton's law of cooling, if I let y of t be the temperature of my object, so the temperature of the dorm room we can think about starting at time midnight in some sense. So t hours after midnight, then I can use Newton's law of cooling in order to set up an appropriate differential equation to solve for this function y of t. So dy dt, so the law says the rate of cooling of the dorm room is proportional to, so proportional to tells me that I want to put in a constant, and because it's cooling, I'm going to put a minus k there, and it's proportional to what? Here, it's not just proportional to the temperature of the dorm room, it's proportional to the difference between the temperature of the object and the temperature of its surroundings. So the temperature of the object, so I'm going to put my difference in here, the temperature of the object is y. And that's varying. The temperature of the surroundings in this instance is 35. That's the temperature of the outside. So I'll point out Newton's law of cooling always takes on this structure where you have the variable here and you have a constant that represents the the surrounding temperature there. Sometimes you might be provided with the value of the proportionality constant, but we'll see here we don't need that because we can solve for it from the given information. But again, importantly, this is separable. Just like the previous example, this one depends only on the dependent variable y, which automatically is separable. And we have a few choices for how we want to separate that. I'm going to choose to bring this over here and leave the minus k on the dt side. Alternatively, you could bring the minus k over with y. It doesn't matter. So once I do this, I'm going to anti-differentiate both sides. And in doing so, I get the natural log of y minus 35 in absolute value on the left-hand side. And I get minus kt plus an integration constant c on the right-hand side. If I want to solve for y, I'm going to raise e to both sides, giving me y minus 35 on the left and ce to the minus kt on the right. And finally, I'm going to add 35 to both sides. So my general function is going to look like this. What we can take advantage of is two pieces of information. we know that at time 0, which is midnight, the temperature is 76. So if I plug in 0 to my solution function, I get C plus 35. We want that to equal 76, so C is going to be 41. So I can update my solution function to reflect that value of C. I still, at this point, don't know the value of K, but we also know that 1 hour later, the temperature is 65. So that means when I plug in 1 to my solution, which I would get 41 e to the minus k plus 35, that should equal 65. And we want to solve for k. So we can subtract 35 from both sides to get 41 e to the minus k equals 30. If I divide both sides by 41, we'll get e to the minus k equals 30 divided by 41. Minus k therefore equals the natural log of 30 over 41. And therefore k is equal to minus the natural log of 30 over 41, which is roughly 0.312. So that means that my temperature function could be expressed as 41 times e to the minus 0.312 t plus 35. So that is my solution function. In terms of what we're looking at, so then to decide or predict what the temperature would be at 7 a.m., all we would need to do is go back to this equation and replace t with 7 to reflect 7 hours after midnight. That would then give me 41 e to the minus 0.312 times 7 plus 35. And if I were to evaluate that in a calculator, that would give us roughly 39.6 degrees Fahrenheit. So it would end up being pretty cold from that.